Welcome to Lecture 10, and we will be talking about stereochemistry. We are in Chapter 5 of our textbook, and the first thing we'll start off with is terms. So we'll talk about the terms in the chapter. You have to understand your vocabulary for stereochemistry, and so we'll hit the terms. The other learning objective for this lecture will be being able to locate and identify a stereocenter. A stereocenter is also known as an asymmetric carbon, and I will tell you how to do that. We will also look at configuration, and you'll need to be able to assign configuration, and that's R or S to these stereocenters. So once you can identify a stereocenter, you got to give it a name. It's going to be R or S, and we'll talk about how to do that. And then we'll talk about whether a molecule has a plane of symmetry. And if it does have a plane of symmetry, we'll learn that that makes that molecule achiral, and that's without chirality. So when we learn our terms between chiral compounds and achiral, we'll be able to describe the molecule. So we are describing organic compounds. And so those are the topics we'll talk about first. I'm also going to pull up your lecture slides so you can pull those up and take notes. And then we're going to finish off with working POGIL in your POGIL activity book. We'll look at the models 1, 2, models 1 and 2 for the stereochemistry. So this is your POGIL activity 7, page 80, and that's stereochemistry. And we'll do models 1 and 2 in this segment. Okay, so first let's look at your terms. So if a molecule is chiral, chiral means handedness. And so if you look at your hand, so if you put your hand and you put your hands together, so if we were sitting in the classroom, I would have you put your hands together, and I would say your hand is chiral. Okay, it actually means handedness, and that means if you put a left-handed glove on your right hand, it wouldn't fit, and the right-handed glove wouldn't fit the left hand. This is very important because our biological receptors can distinguish between different molecules, just like your hands, between chiral molecules. So I don't have the structure in front of me, but if you look up the structures for caraway and you look up spearmint, these are two different scents. They smell different, they taste different, right? Caraway seeds versus spearmint. Well, they're kind of like your right and left hand. If you actually look at their structures, you would see, and you could Wikipedia that, you would see that they only differ by one carbon. So one carbon atom, they differ, and just like your hand, and they are, well, we're going to learn a word. So these are both, this is a chiral molecule, and this is a chiral molecule, okay? And what does it mean to be a chiral molecule? It means that you can rotate, that molecule rotates plane polarized light. So you can work some problems where you can do this lab experiment and you can actually measure how much of these molecules rotate plane polarized light. I do have some problems for you on that. We're not going to go into that in your book so much, but if you put these molecules in a polarimeter, you would put it in a cell. This is a cell, and you regular light has light waves that go in all directions. But if you put it in a polarizable and you polarize the light where you get only the light coming in one direction, okay, so your light, H nu, is coming in one direction. When you hit a molecule that's in this cell and it has an asymmetric carbon, so let's say we have an asymmetric carbon, we'll say this is our asymmetric carbon, and you have a lot of those molecules, what will happen is this light molecule might be progressing in one direction, and then all of a sudden it hits this molecule and it'll start progressing at an angle, okay? And so a polarimeter can detect that and say, okay, the light has been rotated by 20 degrees. And that is what a chiral molecule can do. It can rotate plane polarized light. And so caraway and spearmint, they differ by one carbon, just like your right and left hand. So these are chiral molecules, and they have different properties. And our biological receptors in our nose and our body can interact with one enantiomer. That's another word you need to learn. Let's see if you have all these. Yeah, these words are in the beginning of your chapter. Enantiomer. An enantiomer is like caraway and spearmint. Enantiomers are compounds that are mirror images of each other. See the exact words. Let me see. Asymmetric carbon. Do you see an enantiomer? Okay, an enantiomer. I'm on page 240. They're mirror images, isomers. So they're a pair of compounds that are non-superimposable. So they're called non-superimposable mirror images. Okay, so if you want an example of an enantiomer, your right and left hand, okay, are enantiomers. That's going to be a very important word. So your right and left hand, they're mirror images of each other. And you're going to have to learn how to do this. And then you take one, so if you take your right hand and you rotate it, so I'm doing this right now, I take my right hand and I rotate it. And now I wiggle my thumbs. Do you see how the mirror images are not superimposable? Because my left hand has my thumb pointing at me and my right hand now has my thumb pointing away from me. Now, why is this important? Well, you've learned a little bit about dashes and wedges. So if you take a compound that has a stereocenter, let's see, so if we have this as a stereocenter, you see how that goes away, and then if you had a mirror image of this, maybe well, let's make it simple. Okay, so let's take this carbon, put CH3 there, hydrogen there. Okay, so those are in the plane, those lines. And if this comes at you, and we put a bromine there, then this goes back, we put a fluorine there. Okay, so this compound has an asymmetric carbon. And so an asymmetric carbon is a carbon bonded to 4 different groups. Okay, so you have to be able to find those asymmetric carbon. So what is that carbon bonded to? It's bonded to a CH3, it's bonded to a fluorine, it's bonded to a hydrogen, and a bromine. Do you see how each 4 of these are different? So that makes that an asymmetric carbon. If a compound has an asymmetric carbon, this is also called a chiral carbon. And if a compound has one asymmetric carbon, then it is going to be a chiral molecule. And what does that mean? That means if you put it in a cell and you shine plane polarized light, it will rotate plane polarized light. Now, that means it also has an enantiomer, just like your right hand has a left hand. And so what would the enantiomer look like? Well, let's make this our mirror, okay? And you have to learn how to draw these mirror images. So to draw a mirror image, you actually, the CH3 here, what's in the plane, and the hydrogen goes back like that, and then you just draw what's on the wedge and what's on the dash. And like I said earlier, if you've caught it, you always want your dashes and wedges on the same side. So this is the mirror image. Now, these are non-superposable mirror images. So take your right and left hand and look at it and have them looking at each other, and then take your hand, your right hand, and rotate it. Wiggle your thumbs. Okay, so what is coming at you here, okay, that's coming at you, is going to be going away. So when this rotates, you don't flip it, you rotate it 180 degrees like your hand. You can't flip your hand, you rotate your hand. And so then you redraw this, and you only want to redraw the mirror image. Okay, this is your original compound. Don't redraw that, leave that there. So when you redraw this, you're going to have the carbon. Here, let's erase this here. Okay, so when you redraw this, you're going to have the carbon, the CH3, what's in the plane. You see this in the plane? And the hydrogen. Okay, now what is forward, so this red that was forward is now going to go in back. And what is in back now becomes forward. So you just switch what's on the dash and the wedge. Okay, let's write that down because you have to know how to draw these mirror images. So we'll write to draw a mirror image. Okay, so I draw my little mirror here, and then you draw it here just like the desk, but when you rotate it. So then you draw the mirror image and then you rotate the mirror image. And when you do this, you put what's on the dash, so what is in front goes in back. What is on the dash, I'm sorry, that's a wedge. The dash is what's in back. So your back goes in front. Okay, so the dash becomes the wedge becomes the dash, and then what is right becomes left, and what is left becomes right. So you see that right here, the CH3, the hydrogen's on the right, and when you rotate this, now the hydrogen's on the left. So what is on the right becomes left. The bromine was on the wedge, now becomes the dash. The fluorine, which is on the dash, becomes the wedge. If you don't believe me, put out your hands. Okay, make the mirror image of your right and left hand. Now, your thumb is pointing towards you. Okay, that your thumb is on your wedge. Your pinky, move your pinky. Your pinky is on your dash because it's going away from your body. Now take the one mirror image, your right hand, and rotate it. If you had to redraw that mirror image, now where's your thumb? Wiggle that right thumb. That's going away. So the wedge now became the dash, and your pinky, wiggle your pinky. Your pinky was on the dash and now becomes your wedge. And so, one, you draw the mirror image, and then you have to ask yourself, are these superimposable? And so then what you're comparing is, you're comparing this first molecule that you didn't really touch to this molecule. And you compare these two. Are they the same? No. See, the bromine's in the back and fluorine's in the front. Okay, so just like your hands are not superimposable, either of these two compounds. And that's because they had a stereocenter. Now, if you did this for a compound that didn't have a stereocenter, so let's just take Okay, so let's take bromine here and chlorine here and CH3 here. Okay, so this is a carbon and it is bonded to CH3, CH3, fluorine, and bromine. You see how these are the two same things? Okay, so what happens is if you did the mirror image here, and then you rotate 180 degrees, so what's on the right becomes the left, what's on the wedge becomes the dash, and you compare these two molecules, you see the CH3s are on the same size, okay? So those are superimposable. You can just basically, you could turn this and you could superimpose those. Okay. Um, so this molecule would be achiral. And that would mean its mirror image is superimposable. Okay, so going to your slides, stereoisomers. Um, there's some examples there. Any molecule that is chiral must have an enantiomer. Asymmetric carbon is a carbon that is bonded to 4 different groups. So you look at the carbon and you see that that carbon is bonded to 1, 2, 3 groups, not 4. Anytime you get, so if you have a molecule like this, you're going to have molecules like this, okay? And you have to decide let's see, how many asymmetric carbons are there? Okay, so you might get a question, how many number of asymmetric carbons? Well, let me just tell you, CH2s, that carbon is bonded to 2 hydrogens. So that's not asymmetric. What about CH3? Okay, and we're just looking at carbon. Okay, so let's look at carbon. That carbon is bonded to 3 hydrogens. So that's not asymmetric. So basically you're going to look at carbon, which is quaternary, bonded to 4 different groups that are not carbon, or that could be, or it could be carbon, but bonded to 4 and no hydrogens. So a quaternary carbon has no hydrogens. And then you can have a methine, which is a CH, and that would be bonded to 1 hydrogen. So you see the CH3, you don't have to worry about that. This carbon is bonded twice to oxygen. Okay, so that cannot be, so that's an sp2. So you're really looking at a methine or quaternary carbon, and that would be an sp3 carbon. This carbon here, okay, this carbon is an asymmetric carbon. Okay, what groups is it bonded to? 1. And then what you do is you go out. These are the same, but these are different. Okay, so you go out, you move out. So this is different than this. And because those are different, this is an asymmetric carbon. Okay, so that's an asymmetric carbon. Put those in blue. You go here to this CH2, we'll just go around. That's a CH2. Okay, it's carbon bonded to carbons, not worry. CH2, not worry. Okay, what about this one? This is a CH. Okay, so if you want to draw the H in there, you can. All right, so you're bonded to an H. You're bonded to another carbon that's bonded to an H, which is different than a H. And then you got a CH2. Okay, so you got to go CH2, CH2, and then the point of difference, CH2 and a carbonyl. So those are 2 different groups because you're looking at the whole group. 1, 2, 3, 4. So yes, that would be another asymmetric carbon. Okay, so far we got 2. Let's keep going. We don't have to worry about this one because that's CH2. This one's carbon bonded to two oxygens. Don't have to worry about that one. This is a CH2. What about this one? That's a CH. So we got H. We can even highlight. We got the H. This group is different. That group is different. And that group's different. Okay, that's a CH and that's a CH2. So that would be an asymmetric carbon. Okay. Okay, that's an asymmetric carbon. Here, we go to this one. That's bonded to two carbons. Okay, that's an sp2 carbon, so we don't have to worry about that. This carbon here, same thing, sp2 carbon. We don't have to worry about that one. Okay, you come to this one, and we now have the H. We have this CH. This is a CH2, and this is a CH bonded. So this group is very different than this group. So yes, that would be an asymmetric carbon. So that would be an asymmetric carbon. And then we're keeping on working around the molecule. This is CH2. So how many do we have? We have 1, 2, 3, 4. So there's 4 asymmetric carbons in this molecule. And that's the kind of questions you might get on quizzes and tests, on exams. How many asymmetric carbons are in this molecule? 0, 1, 2, 3. Okay. You need to practice that. So asymmetric carbons are what? They're carbon atom that's bonded to 4 different groups. That would be a chiral carbon. That means it can rotate. The molecule is going to have an enantiomer. Okay. And it will also, we'll learn about stereo chemistry and diastereomers, meso compounds. So we're going to be building on this concept. But the first thing you need to be able to do is recognize an asymmetric carbon, because that's a carbon bonded to 4 different groups. And a molecule can have many asymmetric carbons. When I worked at Eli Lilly, and my favorite compound that I actually have a patent for, it was for prostate cancer. It took 18 reaction steps, sequences to make, and it had 3 asymmetric centers. So 3 stereo centers. Asymmetric centers, stereo centers, chiral carbons, these are also known as. They're just exchangeable. Sometimes stereochemistry can be challenging because you have a lot of vocabulary. So moving through the slides, that's kind of what they're talking about, stereogenic atom. You have some examples of chiral carbons. Like I said, if you have to draw the mirror image and rotate the molecule and to see if it's superimposable, that determines whether a compound is an enantiomer. Okay. Now, if there's a plane of symmetry at any point, that would be an achiral carbon. An achiral compound. Usually, when you use the word chiral and achiral, okay, it's describing the molecule as a whole, okay, the entire molecule. And this means doesn't rotate plane polarized light. Okay, this does rotate. And so experimentally, that's how you determine whether a compound is chiral or achiral. Now, a chiral compound can have stereocenters. So you take something like this. Well, let's do this. Let me give you this one. Okay. In your book, you have this example. This is a good example. So if you have a 5-membered ring and you have the chlorines on bottom, okay, and the hydrogens on top. Now, how would you draw this in a 2-dimensional flat? You would draw the chlorine or the hydrogen, probably draw it like this. Okay, Cl, Cl, okay, You should probably draw it like that. Let me make it a little nicer. Okay. And this is more of a 3D image, right? This is how you do the two-dimensional. Now, a plane of symmetry. That means if you took this molecule and you folded it in half, do you see how they are the same on both sides? Okay, this is a plane of symmetry. So, are there any asymmetric carbons in this molecule? Well, let's look at this carbon. This carbon is bonded to a hydrogen, a chlorine, a CHCl, and a CH2. So yes, you would say, yes, that's an asymmetric carbon right there, and this is an asymmetric carbon. So it has two asymmetric carbons. But that doesn't mean that it's a chiral molecule. This is an achiral molecule, folks. It does not rotate plane polarized light because it has a plane of symmetry. So I'm looking on page 243 in your textbook, and it says any molecule that has an internal plane of symmetry cannot be chiral, even though it may contain asymmetric carbon atoms. Okay, so you got to look for the plane of symmetry. You always want to do that check. Now, and there's some examples of achiral compounds. The other thing I need to teach you is how to name these. We're going to name the asymmetric carbons in a molecule. And we name them as R or S. And this is page 244. This is called configuration. So configuration. If you sign configuration, then you have to sign R and S. This is different than what you did in chapter 3. We did conformations. Conformation is the chair conformation, and that's the rotation around a bond. So configuration would be two different molecules. They're different, okay? So you have twins, and you have one named Bob and one named Bill. They might be very similar, but they're different. Now, conformate, that would be configuration. They're different. They're different. R is different than S. That's why it gets a different name. A conformation is if Bill is laying on the bed and then Bill is sitting in a chair. It's still Bill, but Bill is in a different conformation. And so when we do these organic molecules and you have a cyclohexane molecule and it's in that conformation, the chair versus the boat, okay, those are different conformations, but it's still the name cyclohexane, okay? You start doing chiral molecules, you have to assign an RS, and they're different molecules. And so I need to teach you how to name them. And we use let's go for another page. We use what's called the Cahn-Ingold Krylog convention. Okay, it's the most widely accepted naming. So first thing we have to do when we're doing naming configuration, step 1 is we're going to assign priorities. Okay, so a priority, you might want to get a periodic table out. And so it's based on higher atomic number. So if you look at the halogen, so if you have a molecule like this, all right, so we have 4 different groups here. We have this group, we have this group, we have this group, and we have this group. So is that an asymmetric carbon? Yep, you betcha. So we have an asymmetric carbon. So when we have an asymmetric carbon, a carbon bonded to 4 different groups, we need to assign a configuration. Now I'm going to make this a wedge and this a dash. Is this R or S? Okay. So what would the name of this compound be? This is an alcohol, and it has 1, 2 carbon. 1, 2. So 1, 2 carbons. So let me name it. I like it because that's what we're trying to do, name. So 2 carbons. What's 2 carbons? Ethane, right? Well, this is an alcohol, so we're going to drop the E and add OL. It's on carbon number 1. So ethane 1-ol. That tells me the OH is coming off of carbon number 1. And then we have the substituents coming off of carbon number 1. So 1, A, B, C, D, E, F, G, H, I, F comes first, alphabetical 1, fluoro, dash 1, iodo, SN 1-ol. Okay, that's the name, but it's not totally correct because we have to include parentheses, and on carbon number 1, I put a blank there, 1 blank. We have to decide, is this an R or is this an S? Okay, in the name. And that's how we follow the Kohn-Ingold-Prelog convention. So the first thing you have to assign priorities once you find the asymmetric carbon. So which one has a higher atomic number? Yes, iodide. So this would be number 1. And then you're comparing just the direct elements on this carbon. So carbon, iodide, fluorine, or oxygen. Okay, iodide, if I look at iodide on the periodic table, it's like 127. Okay, fluorine is 19. Carbon is 12 atomic numbers. Oxygen is 16. So we have iodide is 1, and then fluorine would be 2, and then oxygen would be 3, and then 12 would be number 4. Okay, so atoms with higher atomic numbers receive higher priorities. And it gives you an example there. And then it also shows you if you have to do a tiebreaker. And I'll show you an example of that next, okay? So let's go on to step 2. Okay, so step 2. Now we have to connect 1, 2, 3. Okay, so we're going to connect these. We've got to decide when you connect 1, 2, 3. So if you connect 1, 2, 3, and this arrow, I always think I pretend like I'm driving a car, and I'm turning the steering wheel, and I'm turning the steering wheel in this direction. I'm going which way, right or left? Yes, I'm going right. So that's R. If I connect 1, 2, 3, excuse me. So if I have 1, 2, 3 this way, and I connect them this way, okay, so I have to go this way to connect. 1, 2, 3. I got my steering wheel. What am I doing now? I'm turning left, right? And left is S. Now they also do clockwise, but this is nowadays people don't use the hand clocks, and this is counterclockwise. Okay, so right or left. These are German words. If you look in your book, you'll see how to say the German words. Anyway, what is it? Oh yeah, so S is Latin for sinister. So sinister, which means left. And R is Latin for rectus. Okay, rectus, and that means right. Okay, now what is this compound? Let's look. So I'm going to connect them. Okay, so I'm going to find 1. There's my 1. There's my 2. There's my 3. And I always think I'm like connecting the dots. We ignore 4 right now. Okay. So this is step 2. We connect the 1, 2, 3, and then so which way are we turning the steering wheel? Yes, we're going right, aren't we? Now, step number 3. So we've assigned priorities. We've decided whether it's clockwise or counterclockwise. Now, then you got to do step 3 is for your lowest priority. Is it in the back? Okay. If it's in the back of the molecule, then R stays R and S stays S. Okay, so whatever you assign them to. But if it's not, the answer is no. So this is yes. If your answer is no, you got to do a switcheroo. Now normally we would have some molecules out. And so if you actually did this molecule and you held it in your hand, you would hold the priority number 4 in the back. And then you would see fluorine is at the top. So your eyeball's here, okay? And you're looking that way, okay? Because fluorine's in the back, or CH3 is in the back. And then you see you've got to go from fluorine to iodide to the oxygen, and that still puts the CH3 in the back. So yes, in that case, this is R. And you do want to practice some examples on that. Okay, so let's see. Let's go back. Let's now look at what if we have a tiebreaker. Okay, so I'm going to give you another example. Let's do this example. Okay, first thing we have to do is we have to determine where our asymmetric carbons are. So the first carbon here is a CH2. So we go on, right? CH2. We have a CH, okay? So we have this as a CH, and then this other one is a CH3. So is this carbon here bonded to 4 different things? It's bonded to hydrogen, it's bonded to bromine, it's bonded to CH3, and this group here. Okay, so it's bonded to H, CH3, Br, CH2, CH2, Br. So are those 4 different things? Yes. So there's your asymmetric carbon. Okay, so if we draw these, where this is in your plane, this bromine's here, excuse me, and we have CH3 here. We're going to put that on the wedge, and then we put this on the dash. Okay, now I'm going to draw the mirror image. Okay, so it has one asymmetric, these are going to be enantiomers of each other. Okay, so one of them, enantiomers. That means they are, what are they? Say the non-superimposable mirror images. That means one's an R and the other is an S. Okay? It means they are chiral molecules. They rotate plane polarized light. So now I'm going to draw the mirror image. CH2, CH2, Br, Br here. On the wedge coming at me is CH3, and this is H. Okay, now if you wanted to rotate that and see that these were, you wanted to rotate that 180, then you would make sure that, let's just go ahead and do that. CH2, CH2, Br. Here's your carbon. See the bromine's on the right here. The bromine would be on the left. You got CH3 You can put your dashes and wedges here. CH3 would now be on the dash, and H would be on the wedge, and then you would compare these two. You would compare these. And you would see that these are the same, okay? But the CH3 and the H are non-superimposable. Okay, so that's how you draw the mirror image. There's your asymmetric carbon. But we're going to go ahead and we want to assign R and S to these molecules. So we're going to be looking at assigning this one and this one. Okay, we're not worried about that mirror image. Okay, so assign priorities. So get out your periodic table. What's number one? You've got a carbon, hydrogen, carbon, and bromine. So bromine, oh, I did molecular weights. You know, it doesn't matter, but there's 35. You can do either way. It works out. So bromine would be number one. All right. Number two, it's carbon, right? Carbon is atomic number 6, or you can do molecular mass. Okay, so we have a tie. So you got to go to the next. So this carbon is bonded to 3 hydrogens. So the next one would be a hydrogen. This carbon is bonded to 2 hydrogens and 1 carbon. So what's higher ranking? The carbon. So you would compare the carbon here, and this next highest ranking is a hydrogen. So you're comparing a carbon versus a hydrogen. Okay, so obviously this is the winner. Okay, so that gets the 2, and that means the CH3 gets the 3, and the 4 gets the hydrogen, which has an atomic mass of 1. Second step is you connect the 1, 2, 3. 1, 2, 3. Okay, you turn the steering wheel. R. So this is your R enantiomer. Okay, let's go do this over here. So here's your carbon. Bromine gets 1. This gets 2. CH3 gets 3 and 4. And then you do connect the 1, 2, 3. Okay, 1, 2, 3, and that is S. Notice your hydrogen, step 3, hydrogen, your lowest priority, is it in the back? It's going away? Yes. So back stays back. So these are enantiomers of each other. Let's do another example where I just give it to you and you sign R and S. Okay. Okay, this is a good one here. Okay, so let's just do this one example and then we'll go on to cyclic compounds. I will do the POGL activity on a separate lecture because this is a lot. All right, so let's assign R and S to this. So do you see this is your asymmetric carbon? So this molecule has 1 asymmetric carbon because the other ones are CH2, CH3, and CH3. Now we need to decide, is this R or S? And let's just go ahead and name it. 1, 2, 3, 4. 4 is butane. This is an alcohol, and it's on carbon number 2. So this is butan 2-all. Okay, and then we want to decide, is this RS? So you need to put RS there. Well, let's assign our priorities. We're comparing oxygen, carbon, carbon, hydrogen. So oxygen is atomic number 8. So this is number 1. Now we're comparing carbon and carbon. So that's a tie. Then you got to say, what's the next highest priority on this carbon? Another carbon. This one is a hydrogen. So you're comparing now hydrogen to a carbon. Carbon wins the tiebreaker. This is number 2. And then this would be number 3. And hydrogen with its atomic number of 1 is 4. Then step number 2, you connect the 1, 2, 3. 1, 2, 3. And that would give you, turning the steering wheel to the left. Left is S, counterclockwise. So, but then you have to do your check. Is priority number 4 the lowest priority? Priority in back? Is it on the dash? Nope, it's on the wedge. It's coming at you. So you have to do a switcheroo. Okay, and the switcheroo means S now becomes, and I do like that, S now becomes R. So this molecule is not S because we had to do a switcheroo. It's an R configuration. Okay, so you need to work those. What about cyclic compounds? Okay, so here's S-carvone. Let's look at this molecule real quickly. This is a natural product. Okay, now where's your asymmetric carbon? Let's check every carbon. Okay, so this is CH3, it's not. This is a C double bond O. This is a C double bond carbon, so that can't be. That's C double bond carbon. This is a CH2, this is a CH2. This is a CH2, that's a carbon, double bonded carbon. This is a CH3. So the only asymmetric carbon is this carbon here. That carbon's bonded to a hydrogen. It's bonded to another group here. Okay, it's bonded to this over group here and this group here. Okay, so those are different groups. So that's your asymmetric carbon. Now we have to assign priorities. Okay, so hydrogen is 4 because it has an atomic number of 1. And now we have a carbon, carbon, carbon. So we got a tie. And then when you have a double bond like this carbon here is bonded to 1, 2, 3 carbons. So that carbon gets 3 carbons. This carbon here is bonded to 1 carbon. This bond is bonded to 1 carbon. Okay, so 3 carbons beats 1 carbon. It's like rock, paper, scissors. So this would be number 1. So this gets 1 priority. Okay, so there's 1. Okay, we already said this is number 4. So now we got to decide which one's 2 and which one's 3. So we got to go to the tiebreaker. So we go on to the next one because these are CH2, CH2s. They're the same. So you go here. This one's a 2C. This is bonded out to 2 carbons. All right. This carbon here is bonded out to 2 oxygens. Well, carbon's what? Atomic number 6. Oxygen's 8. So this side here gets the number 2, and this would get number 3. Now we connect the dots. 1, 2, 3. So how do we turn the steering wheel? Counterclockwise to the left. Are we going left? So that's S. And then we check. Is priority number 4 in the back? Yes. So S stays S. Okay. And that should help you there. Just kind of finishing up on the slides. Properties of enantiomers. Enantiomers properties are like boiling points and melting points. Enantiomers have the same. So an R and an S, that's the only difference. One asymmetric carbon, they're mirror images of each other. They're non-superimposable. They're going to have the same density. Okay, they're going to have the same melting point and the same boiling point. Okay, but they're going to rotate plane polarized light. So when you do the rotation of the light in the plane, one of them is going to rotate maybe, let's say, 20 degrees magnitude. This is called magnitude, the number, in the right direction, whereas the other enantiomer will go 20 degrees in the opposite. So they rotate light equal in magnitude, so they're going to do the same degrees, but opposite in direction. So that is how how enantiomers' physical properties are different. They have same melting points, same boiling points, same densities, but they rotate plane polarized light in different directions. And they also interact, so that's one thing they do different. The second thing they do different is they interact with biological receptors. Okay, so if they're interacting with a chiral compound that can determine right from left, R and S, they're going to have different properties. Your taste buds and your scent receptors are chiral, so they can determine and they'll interact differently. And so you have some slides on polarized light and optical activity. Now note that when things are D and L and they rotate light to the right, which is D, or you get a negative L, that is not related to R and S. Okay, so R and S has to be determined by X-ray crystallography. So there are some math in there that you can learn how to solve those problems. I've given you examples. Like I said, I'm not going to give you those mathematical problems on your quizzes or your exams. So you're good there, but you should work through them because you'll have them on sapling. And one other word before terminology before we leave is called racemic. A racemic mixture. Okay, a racemic mixture will rotate plane polarized light by 0 degrees. Okay, and that means there's 50% of one enantiomer, let's say R, and 50% of S. So what's happening is if you have a racemic mixture, even though you might have chiral molecules in there, the molecules may be rotating it R by 20 degrees. The S is rotating it by 20 degrees to the left. And the result is you get 0. So this would be a plus 20. This would be a minus 20. They cancel out, and it looks like you have no chiral molecules, but you really have a racemic mixture. Okay. And so a lot of these times you have to figure out optical purities in the laboratory. So we'll go from here to working our POGIL exercise, stereochemistry, class activity 7.